Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to talk about 3.50 Lewis dot diagrams. Now, in order to continue, we're going to go back a little bit and review. So we talked about initially isotope symbols. B11 for boron. This would be the isotope boron that has 11 things in the nucleus, and 5 of them would be protons and 6 of them would be neutrons. But that's about all I could tell about that. So we came up with the nuclide symbol. Gives us a lot more information. It tells us that it's boron, the number of neutrons, the protons, and it also tells us the ionic charge. Now in this case, it has a blank in the top right corner, so it's going to be a neutral atom. And that means that the number of protons is going to be equal to the number of electrons. In this case, both of them would be 5. Now, it also can happen if we changed it to a +3, which means it's now a cation. We change the charge, and the number of electrons would then be 2. Now, I don't have it edited here, but we can get the idea. Then we started talking about the Bohr model. This gives us an idea of actually what the atom looks like. So, the Bohr model told us the ionic charge. It told us that the number of electrons in this case was 5. And we found out that for boron, we have 2 energy levels since it's in period 2. And we said that according to the Bohr model, that there are 2 electrons on the first energy level and 3 on the second energy level. Now, we're going to come up with a new term called the valence electrons. We'll explain those in the next slide. So what exactly are valence electrons? These are electrons on the outermost energy level. That is how we're going to define our valence electron. So in this case, our second energy level is going to be our outermost energy level. And I have 3 electrons on here. So my number of valence electrons is going to be 3. Now, what are the valence electrons? These are electrons that are shared or given away when elements make compounds. Now, there's nothing particularly special about these. The only thing is their location. All electrons are the same. They're all made up of the same things. The only difference is that these are in the outermost ring. Now, one of the things we have to pay attention to, and a lot of students miss this, is the maximum number of valence electrons is 8. Now, that gives us or leads us to a rule of 8. It says that atoms are happy when they have 8 valence electrons. Yes, I know that atoms don't have emotions, but we're going to pretend that they do for this case. So, again, the rule of 8 states that atoms are happy when they have 8 valence electrons. Now, who is happy? Well, let's look. Here's all of our elements on most of the periodic table. I left out the bottom part here, but you'll get the idea. So who's happy? Well, let's put the number of valence electrons in each group. So the hydrogens, they are going to have 1 valence electron. Beryllium, okay, they're going to have 2. The transition metals, they're going to have various numbers of valence electrons. We'll talk about those a little later. And then we have boron is 3, carbon 4, nitrogen group is 5, oxygen group is 6, the halogen group is 7, and the noble gases is 8. So, of all of these, the only ones that are actually happy are the elements in group 8A. Now, these are all my neutral atoms. And the only ones, again, that are happy are my noble gases in group 8A. Does that mean that the rest of the elements can't be happy? No, not really. They can be happy, but they have to do some things. So first of all, we're going to look at our cations. Remember we said cations are positive ions. And how do they become positive? Well, they end up giving away electrons, so they have more protons than electrons. So our cations have 1, 2, various, 3, and 4 valence electrons. These are electrons on the outer ring. Now, the cations can either, let's look at sodium for instance, sodium can either gain 7 electrons to be happy or give away 1 electron to be happy. Now, sodium isn't all that strong, so it cannot hold 8 electrons on its third energy level. So it's going to end up giving up that electron on the third energy level and then drop back down to the energy level 2. And we'll see an example of this in a little bit with sodium. So where do all those electrons go? Well, they tend to go to anions. Anions are going to be the opposite. Instead of losing electrons, they're going to actually gain electrons. So let's look at nitrogen, for instance. Nitrogen has 5 valence electrons, so it can get to 8 by gaining 3. Much easier to gain 3 than to lose 5. So the anions are actually going to be gaining electrons. And this is where we get to when we talk about our next section, which is going to be compounds. This is what happens. It's the valence electrons that are actually transferred, shared, or just given away when we make compounds. Again, we'll talk about that in the next unit. Now, here's one thing I want you to see that's kind of interesting on the periodic table, is that the number of valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, is actually the same as the group numbers of the A groups. So 1A has one valence electron, 2A has 2 valence electrons, 3A has 3, and 4A has 4, and 5A has 5, 6A has 6, 7A has 7, and 8A has 8. Now, helium is an exception to that. It can only handle 2, but that's okay. We'll talk about small atoms in a little bit. So, how does an atom become happy? Okay, well, it's going to actually end up losing its electrons. So there's 1 that's lost for boron. There's 2 that's lost. There's 3 that's lost. Now, boron has only 2 valence electrons. It's going to be a cation, and it's going to be happy. Now, you'll say, well, wait a minute, it doesn't have 8 valence electrons. Well, and there's always exceptions to the rule. Now, we have small atoms like helium through carbon. Now, boron falls in that category, that are happy with just 2 valence electrons. So that is good. Now, you notice here that I didn't say anything about hydrogen. Hydrogen breaks the rule too. So hydrogen is actually happy with no electrons. Bye, electron. Now it's happy. So it has just a proton in an ion of hydrogen. Kind of an interesting thought, that an ion of hydrogen is just a proton. Okay, so we looked at boron, which is a small atom. Let's look at another one that is slightly bigger. Let's look at sodium. Sodium has 11 protons, and it's going to have 11 electrons and when it's neutral. So we have 2 on the first energy level. I have 8 on the second energy level, and then just 1 single one on the third energy level. Now, what's going to happen? How does that become happy? Well, if I take away that last electron on the third energy level, goodbye, it now has 8 electrons on its outer shell. So if we count, we can see that the second energy level now has 8 valence electrons. And guess what? It's now going to be happy. So that's what happens with cations. Let's look and see what happens with anion. So here's an anion of chlorine. Okay, again, chlorine has 17 electrons when it's neutral. There's 2 on the first energy level. There's 8 on the second energy level. And the third energy level is going to have 7. Now 2 plus 8 is 10, plus 7 is equal to 17. Now, this is not happy. It needs to have 8 on its third energy level. So what happens? We add 1 back in, and we then become an ion. And now, if we count, we have 8 electrons on the outer ring of chlorine. That then makes us a happy atom. Now, in 1916, a gentleman by the name of Lewis came up with the idea of studying these valence electrons, and he came up with a way of showing them, and we called it the Lewis dot diagram. So how does it work? Okay, first of all, this just shows the valence electrons. Now remember that the Bohr model shows all of the electrons. The Lewis dot diagram just shows the valence electrons. And why is this so important? Because the valence electrons are the ones that are going to be shared when we get into our next unit. So let's bring back boron. We know that it's in group 3A. So here's how we do this. So we write our element in the middle, B for boron. We're going to draw a box around it. And then we're going to put dots on this box. Now we can't just put them in any place. So we're going to call each side of the box by a clock. And we're going to start it. Are we going to say 12 o'clock and then 3 o'clock, 6 o'clock, 9 o'clock, 12 o'clock? Okay, just like a clock. And then we're going to start placing them at 3 o'clock first, and we're going to go clockwise. So we put 1 at 3 o'clock. We then put 1 at 6 o'clock. We then put our third one at 9 o'clock. So when I take away the clock, this is what a Lewis dot diagram for boron looks like. Okay, let's look at a different one. Okay, go back to chlorine. Okay, chlorine is in group 7A, so that means it's going to have 7 valence electrons. So there's chlorine. Here's my box. Okay, there's our clock. We're going to start at 3 o'clock. We're going to put 1 there, put 1 at 6 o'clock, put 1 at 9 o'clock. We're going to put 1 at 12 o'clock. Now that's 4. We still have 3 more to go. So we're going to put a second one at 3 o'clock. We're going to put a second one at 6 o'clock. And then we'll put another one at 9 o'clock. Now if we count these up, you'll see that we have 7 valence electrons. And our Lewis dot diagram would then look like this. Okay, so let's do one more example. Let's pick oxygen. We haven't seen oxygen lately. So this is in group 6A. So it's going to have 6 valence electrons. There's our O for oxygen. There's our box. Here's our clock. We're going to put 1 at 3. Clockwise, we're going to put 1 at 6. Clockwise, we're going to put 1 at 9. We're going to put 1 at 12. We're going to put the next one, our fifth one, at 3. And then our last one at 6 o'clock. Again, removing the clock, this is what our neutral oxygen would look like. And here's a couple other ones. We're going to look at iron. Now iron we've talked about as being an element that is in the transition elements. In fact, it's in group 8A. Now the 8 really doesn't help us in this at all. All I can tell you is that the transition metals have various amounts, and I would have to tell you what actually type of iron it is. And the way I would do that is I would say, well, this one's going to be iron 2. And what that 2 in Roman numerals means, that means it has 2 valence electrons. So I would write the Lewis dot diagram like this. Fe, there's my clock. Okay, put 1 at 3 o'clock, and then put 1 at 6 o'clock. Now, a lot of my students ask me, do I have to start at 3 o'clock or can I start somewhere else? I just start at 3 o'clock to be consistent. You can start anywhere you want, but you do need to place them counterclockwise, or clockwise, excuse me. You just want to place them clockwise. You cannot put 2 of them right next to each other. That's not the way the electrons actually work. So, let's go to the other type of iron. It's going to be still in group 8A, or 8B, excuse me, and it's going to be called iron 3. So here's my box. Okay, the 3 in Roman numerals tells me that I have 3 valence electrons. There's my clock. 1, 2, 3. So that's what my Lewis dot diagram would look like for iron. Okay, now what would this look like for a cation? Remember, cations are going to make them happy. So I actually have to get rid of 3 electrons. So that's 1. got rid of 2, and got rid of 3 electrons. So now I have an empty box. Really doesn't tell me a whole lot about this iron at all. I don't know what it is. I don't know if I finished it. Did I not finish it? Is it iron 3? Is it iron 2? What is it? Is it a cation? Is it neutral? Don't know. So what I do need to is I actually have to put square brackets around the box, and I have to put the charge of +3 because I lost 3 electrons. Remember, when I lose electrons, the atom now has more protons, and that means it's going to be a +3. So that's what the convention is for a cation. So let's look at what the convention is for an anion. Let's pick chlorine again. And now I have 8 electrons, so it's happy. It's an ion, so I still have to put the bracket around it, and I have to call it a -1. Now let's recap what the Lewis dot diagrams look like. For neutral, 3A. For boron, we're going to draw our box and draw our 3 electrons. Okay, this gets dots around the box, no brackets, and no charge. Okay, then I get a cation. Cations are going to have the element, the box, no dots, brackets, and I'm going to have to show the charge, in this case a +3. So again, no dots, brackets, and a charge. Let's look what an anion looks like. So I have chlorine, Cl, the box, 8 dots, brackets to show that it's an ion, in this case an anion, and the negative charge on the outside. So we do show 8 dots for anions because it's now happy. Okay, it has brackets and the charge. One last thing to remember, the maximum number of valence electrons is 8. Some students decide, you know what, I'm going to put, neon has 10 electrons, I'm going to put 10 dots on this. And they cram 10 dots in on their square. It's not the way it is. Remember, the Lewis dot diagram only shows the 8 valence electrons for neon. So again, this is how they will be shown. Again, notice also that I do not put my dots on the corners. I just put them on the sides of the square. Now, one thing in my research I thought was pretty interesting, and we haven't talked about this. We've talked about the protons being positive. We talked about the electrons being negative. But we really haven't talked about the neutrons a whole lot. And I kind of thought that the neutrons were discovered with the protons way back in the 19-teens somewhere. But that was actually not the case. It wasn't until a guy named Chadwick discovered them in 1932, so quite a bit later, we actually came up with the idea of neutrons. Well, guys, that's all I've got for today. So another edition of Chemistry on the Fly with Mr. F, and as always, have a great day. To tell this, so there is a rule